Okay. So, the last class we did the nucleophilic addition of a primary amine to an aldehyde, and we saw that we get the same nucleophilic addition that we've seen where the nucleophile adds to the electrophilic carbon and one of the protons. Remember, these things are slightly acidic. One of the protons adds the oxygen. That particular intermediate could go forward and continue, and we end up with this product, this imine product. We have these things like hydroxylamine. It looks a lot like a primary amine, and this is the functionality that is nucleophilic, the most nucleophilic on this molecule. And we get a very similar reaction. This is just the R group has become an OH group. We talk about this thing as being an oxime. We won't do much further with that, but we will see today a further reaction. We react hydrazine with aldehydes or ketones, and we get this thing called a hydrazone. There's a couple of different things that are useful about hydrazones. This hydrazone in particular, but also hydrazones where one of these H's, one or more, have been replaced by some organic functionality. What we're going to look at today, we're going to start here anyway, is the reaction of secondary amines with ketones and aldehydes, and that product gives us this thing we call an enamine. Couple of things. So again, this is the reaction of a secondary amine. That means there's two R groups on the nitrogen. We still have to have this proton on the nitrogen. Okay. The other thing we need is a hydrogen on the alpha carbon. And just to remind you, when we use that type of nomenclature, so I'm just going to use an acid. This is the alpha carbon, beta carbon, gamma carbon, and we can keep going, and then at the end, doesn't matter how many we have, we will talk about as the omega carbon. We quite often will talk about alpha and beta functionalities when we're talking about carbonyl compounds. So you need to know you need to know the Greek alphabet up to gamma. And you'll need that for other courses as well. Okay, so here's our carbonyl carbon. This is the alpha carbon. With a secondary amine, the other thing we need for this reaction is a hydrogen on the alpha carbon. So what happens in this reaction, it actually starts off the same for any of it. So here is our nucleophilic portion, and this is the proton. And the first part of the reaction, I'm going to do this. I'll do it with a ketone, and we don't care what these R groups are. And we have some secondary amine. I'm gonna put ethyl groups here again. And we're all familiar with this. We know this takes a couple of steps, and we end up with this compound. So all I've done is added my nucleophile to the electrophilic carbon, and the proton eventually ends up on the oxygen. Okay, and this would be done under acidic conditions. Now, let's say we're doing this in an organic solvent. We're using a catalytic amount of acid. What's the proton carrier going to be in this case, in this reaction? What's going to carry the proton around? It's probably not going to be the conjugate base of the acid. What do we know about amines? Are they basic? They have a lone pair of electrons at nitrogen. Our proton carrier is going to be in this instance, okay? Doesn't matter, but I just want you to start thinking about these things. So in this instance, if we had an organic solvent, now if we were in water or even an alcohol as solvent, that is still the most basic thing, and that's the most stable of the conjugate acids, but other things could act as proton carriers as well. So I want you to start thinking more generally about protons and how they move about and when it's important and when it's not. But most of the time, again, just think that those protons can be carried around by lots of different things in the reaction. So I'm just going to say H plus most of the time, because there's lots of different things that can carry that thing around. So we get to this, and now, and this is what's important. Don't forget this is all reversible. And if we look at this molecule, what's the most basic site on this molecule? Well, it's actually that nitrogen. And if you protonate that nitrogen, you just go back this way. So even though, yes, I know the proton's going to go there most of the time, all that's going to do is lead back this way. The proton, every once in a while, is going to go here. And when it does, and I'll just get rid of our proton carrier over here so as not to confuse us when we're looking at the board afterwards. Okay, so yes, this is the most likely site of protonation, and most of the time this happens and it's going back and forth between a protonated and an unprotonated form on the nitrogen. Every once in a while a proton's going to come and jump on that oxygen, and when it does, it provides a way for this reaction to move forward. So what can happen? We have a lone pair of electrons on this nitrogen. We can just pop those in there, knock our water off. I'm going to do it like this. Could draw it this way. I'll move this up in a second. I'm going to put my oxygen, my hot water that I formed in a box. I just like putting it in a box because it's one of the products. It's an important product for the overall reaction, right? That's one of the products of the reaction. But we don't quite have. Oh, is there anything wrong?
Charge on the nitrogen.
Charge on the nitrogen. Very good. Okay, there we go. So we want to remember to look and see. We're doing this under acid catalysis, so we know we got to have a positive charge around. And once we protonate it, we got to have our positive charge. In this case, our water came off as a neutral molecule, so we still have a positive charge. Now, we have lots of things that can act as a base. So I'm just going to call this base, and our base has a lone pair of electrons. It's probably another diethylamine molecule that's going to be the base, but it's just going to pull off this proton, and when it does, we can move our electrons around and we get this. R, C, R, C, H, and, oops. This is our enamine. So the important things here, the first part of the reaction we're getting pretty good at. We do realize this is the most basic functionality, and it's going to pick up a proton most of the time. That's just taking us back to starting materials. This allows us a way to proceed forward. This is all under equilibrium conditions. If I wanted this as my compound, how would I set up this reaction? I would probably do it in some nice dry organic solvent. So that way I would only have one equivalent of water that's going to favor this equilibrium. If I did this in an aqueous environment, we wouldn't get here, would we? The problem would be that because all these reactions are reversible and we have lots of water around, it would all funnel back the other way. But this does provide us a way to make these enamines. So one of the things you want to get from that is enamines are quasi-stable organic compounds. If we put them in a strong aqueous environment with a bit of acid around, they're going to go back and release whatever our ketone compound was. So that's the mechanism for this. Important takeaways: we need a secondary amine and a carbonyl group with a hydrogen on the alpha carbon. This is just the mechanism that we just did. This is nice. This is the iminium ion intermediate. Okay. Now another thing too. Notice how I push this proton off here and the water off, and then I push these arrows. I could have also had a base come here, form that carbon-oxygen double bond, and knock the water off. That would be a kind of an E2 type of elimination. That's not likely to happen under these conditions, but it certainly is happening at the same time. Both of those routes lead to the same thing. Okay? So the other thing I want you to realize is there are other possibilities for this mechanism. It could go directly from here to here by having this base pull off this proton, form the carbon double bond, and then kick off the water. That would be the equivalent of an E2 elimination. It looks a little weird because you have the positive charge on the water, but that's another potential mechanism that makes sense. So the other thing we want to look at now, so now we're just kind of doing some cleanup for the rest of this chapter. Here's a useful reaction. Sometimes we have a carbonyl group, and we use that carbonyl group maybe to induce some chemistry to happen in different parts of the molecule. And now we want to reduce it to a CH2 group. We have two things. One's called the Clemmensen Reduction. You can look in that named reaction site, and we're not going to get into that. The mechanism's a little goofy, and so we're not going to worry about it. But we can also do something called the Wolff-Kishner reduction. So for this particular compound, we react this with hydrazine, and we end up getting this. This is a hydrazone. We can, under strongly basic conditions, notice now KOH and heat. So some fairly harsh conditions, some strong base and some heat. We have a lot of that that hydrazine around. What's going to happen? We have lots of base around, and we can pull off a proton. I'm going to do it this way. Now what can this particular thing do? We've pulled it off. We have negatively charged nitrogen. What can we do with this?
So is that supposed to be a phenol?
Oh, yes, it should. If it's benzophenone, it should. Yes, sorry. So that's right. We didn't do anything here.
What is the structure of the hydrogen? Just the nitrogen at the top?
Yeah, that's a nitrogen.
How does it? Is it just one nitrogen, or is it two?
No, there's a nitrogen there
What's on? Oh, it's
and a nitrogen there. Sorry, it's this.
yeah.
That's the hydrazone, okay? Sorry. Okay. We can actually draw a resonance structure of this. Okay, that puts that negative charge that's just a resonance structure of that compound on top, where we now have, what did I do wrong here? Okay, right. And we have our water molecule that we formed around, so we can think about this. So we've now put a hydrogen onto that carbon. This is neutral, and we've formed OH minus. So we can now just do this. We're going to pull off this proton. Okay. What is driving this particular reaction? Can anybody think back to last year? Maybe you talked about it in organic chemistry a little bit. We're taking 2 molecules and we're making 3 molecules. Can you think of what's driving this reaction? It's a thermodynamic concept. Entropy. Entropy. So we're producing a gas. N2 is a gas, which is going to come out of solution. So we have a large change in entropy. So that's what favors this particular reaction. We now have this carbanion, and we have some water around. Sorry, I ran out of room. Well, we all know what happens, right? What's that carbanion going to do when it meets the water? Water can act as a base or an acid, can give up a proton. We know we had hydroxide, and we're going to form hydroxide again. We're just going to, the lone pair of electrons are going to pull off that hydrogen, and I'm going to send all this, actually I'm going to send it here. So our final compound is this. Okay, and don't forget we have our N2 gas, which kind of drives this whole reaction. The gas bubbles up, the nitrogen's away. We've done our reduction of our carbonyl compound to this CH2 compound. So this Wolff-Kishner reduction is in that web page I showed you. And again, the mechanism should follow along the same lines roughly, but there may be slight differences. And if you look at your notes and you see slight differences, don't immediately think there's something wrong. Immediately think, do both of these make chemical sense, and take a look at them, right? Are you still pushing the arrows? Do you have bases pulling off protons and things like that? So let me see, a couple of things. I drew a resonance structure here. Another thing we could have done was pull all of this stuff off and have another molecule of water. You may see that happening all at once, although I think that's unlikely because we have 85% hydrazine and not a lot of water. So to set up for that, you will see that in mechanisms, but it may or may, that's happening as well. And here's the mechanism. Oh, in fact, that's right. That's what they did here. Notice how they push everything all at once, and I did it stepwise. Okay, so this can happen, and at the same time, that can happen. So with all of this happening at once, we end up with this thing that I had. And then we have our base again pulling off a proton, forming a nitrogen-nitrogen triple bond, and electrons going to form this carbanion, just like we have on the board, the carbanion. So the only difference was I did this in more than one step. They're showing it as being one step. Now, I say mine is more likely. Why is mine more likely than this? Can anybody think back when you were taught kinetics? This would require 3 molecules to meet at once. We call this a termomolecular type of reaction, right? We have to have our 3 molecules collide and all be in the right orientation. Under the right conditions, that can happen, especially when water is your solvent. But in this case, we actually have 85% hydrazine. So we have a lot of water. This is probably happening, but that's also happening at the same time. Okay, the next thing I want to take a look at is the addition of hydrogen cyanides. Here's our general nucleophilic addition to the carbonyl group again. Our nucleophile and our proton. Our nucleophile adds to the electrophilic carbon. Our proton adds to the oxygen. For hydrogen cyanide, our nucleophile is just CN. Hydrogen cyanide is, it's actually a liquid most of the time, but on a hot day it would be a gas. It's not a very nice gas, very nasty, kill you fairly quickly. So if you ever have to do these reactions, be careful. You won't do them in an undergraduate lab, I can guarantee you, at least not in this country. So here is our general reaction. And notice we're a little bit, we add HCN across and we get this thing we call a cyanohydrin. We can think of it as occurring as our cyanide attacks the carbonyl group to form our tetrahedral anionic intermediate, which would then just find a proton. HCN is a weak acid. I think its pKa is somewhere around 8.3. So how does this occur? Well, we have HCN to give us H plus Cn minus. So our nucleophile is formed in that type of reaction. We can have I'm going to erase up top so we don't get confused here. That was just showing you that we could form our CN. And then we're going to have some HCN around. And that just gives us our products. And regenerates our cyanide, which can go seek out another carbonyl compound and just start this whole thing again. There's our product, there's our starting materials, okay, and it acts kind of as its own catalyst. So the first step of that reaction is typically fairly slow, and the second step is fairly fast. But we actually do this reaction a little differently in practice. We don't use hydrogen cyanide, we use sodium cyanide. Okay, so we just take sodium cyanide, we do this reaction, and we slowly add an acid, H2SO4 perhaps. to protonate this compound, and that can help make the reaction go faster because then we're not dependent on the equilibrium of the HCN. We have all our cyanide there existing as cyanide. This reaction goes much faster this way. You add your acid slowly for a very good reason because you don't want to generate HCN and poison yourself and kill yourself. That's the other reason we use this, is because we don't have to use HCN. We use sodium cyanide, which is a nice, safe salt that you're not going to breathe in and kill yourself with. So, and I tell you, be careful when working with cyanide, okay? Please. Why might we want to make these compounds? We actually make these compounds because they're intermediate to make other useful and interesting things. We can make these things called alpha hydroxy acids. They're used a lot by the cosmetic industry. They're used in chemical peels and whatnot. And that's because the carboxylic acid is a slightly better acid, but it's still a mild enough acid. It'll peel your skin, but it won't give you a severe chemical burn unless you really misuse it. We also can make these things called alpha beta unsaturated acids. They're very nice pharmaceutical intermediates on the way to making other bigger molecules. And the same thing with these beta amino alcohols. These things are both intermediates in the pharmaceutical industry to make drug-like molecules, or leads for drug-like molecules. So they're used quite a lot. I think we have one more reaction to look at. Oh, it's 10 o'clock. Okay, the next thing we're going to do, we're going to talk about these things called ylids. An ylid is, there's different kinds of ylids. There's phosphonium ylids, there's sulfur ylids. What it really means is it's something that has a strong Zwitter ionic character. How many people know what a Zwitter ion is? Okay, a Zwitter ion is a neutral compound that has a positive charge on one side and a negative charge on the other. So it's overall neutral, but we have two sites which are largely ionic. And in this case, we have these phosphorus ylids, okay? You can actually draw a resonance structure for them. So for this particular compound, we have PR3 plus C we can draw a resonance structure which shows a carbon-phosphorus double bond. But calculations and inorganic chemists will tell us this is actually a better representation of this molecule because it is a very polar molecule. And so I'm really, if you think about it, what we're doing is we're taking this lone pair of electrons and throwing them in there to make this carbon-phosphorus double bond. Okay? How do we make these things? We can react an aldehyde or a ketone with these things, and what we get is we're forming a new carbon-carbon double bond. So that's kind of exciting for organic chemists. This person, Widick, was very excited, I'm sure, when he found this reaction because he knew he found a very synthetically useful reaction, and they would name it after him. So I didn't even realize I had that up there. So how do we do this? What do we do with these reactions? We make these things quite easily. All we have to have is an alkyl halide. Alkyl halide. And it must have It has to have a hydrogen on the same carbon as the halogen. So we need a secondary or primary alkyl halide because we need that hydrogen for this reaction to work, for this ylide reaction to work. We can react our alkyl halide with trialkyl or triaryl phosphorus compound. This is the most common reagent we will use, triphenylphosphine. So we have triphenylphosphine, and phosphorus has that lone pair of electrons on it, and we react that with some, I'm going to make it simple, I'm going to react it with this compound, okay? And when we do that, it's just a simple, what kind of reaction is this? Can anybody tell me mechanistically, what do we call this reaction? We have a nucleophile.
SN2.
It is an SN2 reaction. Okay, so we're halfway there, halfway to making our ylide compound. What do you suppose we have to do to complete this ylide? So we want to get to this. What do I have to do to get to there? And I'll help you out a little bit. I'll make it CH2, and I'll put an H down there. What do you suppose I need to do?
So we need, should the positive charge be on the phosphorus?
No. I'm sorry, yes. Good catch. So what do we need to do now to get rid of that hydrogen? What kind of reagent would I need? Base, strong base. And we usually use something, a strong base. Has to be a strong base. And in fact, sometimes we use an organometallic compound, not necessarily Grignard, but we might use butyllithium, a very strong base that will remove this proton and give us our ylide. Okay, now we have our ylide, we make it in situ. We generally do these reactions by making our ylide first. Now remember, we're doing this to react it with a carbonyl compound. And I'm going to react with acetone. So I have my ylide. I'm going to put the lone pair of electrons there. And I'm going to actually set up, let's make it, acetone is fine, doesn't matter. Notice how I've drawn this. So where's our electrophilic carbon? Is the carbonyl oxygen. And the carbonyl carbon is our electrophilic atom. And this is a nucleophile. We're going to attack that. And then we're just going to push our arrows like this. And we end up with this thing. As an intermediate. And we're going to just keep pushing our arrows. How are we going to push our arrows? Okay, so we get this intermediate, doesn't live very long, it quickly decomposes, and we've really just transferred the oxygen from our carbonyl compound. The oxygen gets transferred to the phosphorus, and our methylene group in this case gets transferred to what was the former carbonyl carbon. Okay, so this is kind of a gross mechanism. There's an example, and here's the mechanism as they write it. They use something slightly different, but the same thing. We get this oxyphosphatane intermediate, and we can get rid of push the arrows to get our alkene, okay? And we will get both E and Z isomers if that's a possibility. There are ways of favoring an E or a Z, but we won't get into that. So how do we plan a Widick synthesis? We want to make this compound. So let's just think about this compound and think about what we're actually doing. So we have a carbon-carbon double bond, and we can make that. We need to have a carbonyl group. So we could either make it from this, right? And if we make it from that, we need, this is the other functionality we need. Okay? This would lead to our Widick reagent. We would react with triphenylphosphine, make the Widick reagent, with strong base, and react it with that ketone. Or we could have made it from this. And this compound, right? So all we have to think about is we got to stitch together a carbonyl carbon and a carbon from our Widick, which comes from that alkyl halide. So this is called retrosynthetic analysis, where we start with the molecule we want and we say, what bonds can we disconnect? We disconnect here. We can either disconnect this way or this way. So on your slides, you'll see a little bit, they go right to the ilids. So these are the two ways we could have went, and these are the two compounds that we decided we could have used. And then the synthesis is why we just work backwards. We start off with our alkyl bromide, we react it with triphenylphosphine, we make the phosphonium ion, which we react with a strong base like butyllithium, pull off, in this case, this proton to make our Widick reagent, which then attacks the carbonyl compound and forms that cyclic intermediate, which eventually breaks down into our carbon-carbon double bond. Okay, so that actually, and here's the second route, same thing. Oops, I went the wrong way. We could have used the other reagents as well. One of the things that's interesting, when I was a student, the professor would give us this reaction. This is a reaction that's very much like the Widick reagent. We have an activated hydrogen there. If we use a strong base, we can make this anion. This reaction will go on to make a carbon-carbon double bond. I want you to go out and see if you can find the mechanism for this reaction. Should be fairly easy now. When I was a student, we didn't have Google, didn't have the internet, and you'd have to spend like a day in the library. I found the mechanism for this reaction in less than 20 seconds using Google. So take a look at that. It's called the Horner-Wadsworth Amines. All you have to do is put Horner-Wadsworth Amines into Google and you'll find it. Just take a look at that. What you might want to do is try and see if you can figure out the mechanism and then go searching for it.
Do we need to know every mechanism for Richard?
Only if you want 100%. So, to answer your question, what you will find for my exams and stuff is I have a number of very easy questions, okay? A third of the questions will be very easy. A third of the questions will be medium, and they're not quite bad, and they're fairly consistent. And then a third of the questions become more difficult. Not so much on a midterm. There will always be one question that's hard.
Would those be similar to the ones at the end of the first sequence of it? Where we have to put all the intermediates and the background and we get the end product and we have to build up to it?
To be honest, I'm not likely to ask too many that have more than one or two reactions from a previous course, okay? So the ones on the end of the sapling assignment, I'm not going to ask too many questions like that. That's one of the reasons I told you I'll probably end up taking them off. I want to take a look at them. I still think they're good for you guys because you do have to remember that you need to know the material from Organic 1 to move on in chemistry. But in an exam situation, I'm not going to expect. On homework, you have the entire internet and everything. An exam situation, I'm going to expect you to remember some pretty general reactions from last semester, like an SN2, right? I would expect you to be able to remember a simple nucleophilic substitution reaction, but not something really hairy. So, yeah, to answer your question, do I expect you to know every mechanism? Yes, if you want 100%, you probably have to know every mechanism. Having said that, you can get to 85 and 90% with knowing much less than all of the mechanisms.
Are like the quiz questions like all easy, or like do any of them approach the medium level?
Some of the quiz questions are approaching the medium level. Okay. Some of the quiz questions, there'll be some medium ones. I won't ask what would be considered a real difficult question in any of the quizzes. Well, that's kind of what the homework is about and what the quizzes are about. And I can dig through some old exams and stuff, yeah. Yeah.
You said, I didn't hear you right, did you say you're going to supply old exams to study off of?
I'll look into it. I'll look into it. So I haven't taught this course for about 10 years. I have a bunch of old exams, but they're from a different university and stuff. So I'll find out what the other professors have done in the past.
So would you ask us as a hard question to draw out like a full 5-step mechanism? Or would it be like, here's the...
There would be both. There would be mechanistic questions that I consider fairly hard. Now, having said that, like the steps, we'll see a reaction soon next semester. And we did one here where we did acetal formation. That's kind of a long mechanism, but it's actually not hard if you go through it.
Like the reaction that you just drew out on the board, would we be expected to be able to draw something like that?
The Widick,
Yeah.
I would consider that a tougher mechanism, okay? One of the reasons it's a tougher mechanism is there's some non-intuitive things you have to figure out there. Less intuitive, let's say, okay? For reacting an alcohol with a carbonyl compound where you put 2 molecules of alcohol on, that's all actually the same thing over and over again. It's just a matter of getting them in the right order. Protons jump on, protons jump off, nucleophiles attack, okay? So that I would consider a medium question. Although it's a long medium question, it's a medium question. The Widick there that we just did would be on the order of hard. I would consider that a difficult mechanism.
So something like that could be on the reason.
It could be on the midterm or the final, that's right. And again, the other thing I want you to remember is you're not going to get 5 of those questions, right? There's going to be a bunch of easy ones, a bunch of middle ones, and there'll be some harder ones. And then there's a range of the harder ones, okay? So basically, To get an A+ has to be kind of difficult, but to get to, you know, the B range is really not that difficult. And honestly, the class average for this students entering this from last semester was in the high 70s, so I expect the class average for this course to probably be at least in the high 70s. So you will notice when you go through your here's an example of a mechanism I'm not even going to ask you to do. It's not that hard. If you look at the this is called the Baeyer-Villiger oxidation. Take a look at it. What's interesting is you're taking a ketone and you're kind of inserting an oxygen atom into it to make an ester. It's a very interesting mechanism. Everything goes along. One of the things that's weird, we're not used to seeing these things called peroxy acids. We haven't seen those before. They're better nucleophiles than they are acids. The other thing that's really weird is in the important step is right here. This is really weird. You're actually getting this R group is just jumping over. It's doing what we call a 1-2 shift, okay? This is a difficult mechanism. Everything is fine, and then you get at some point and say, how do I get the R group over there? I'm not even going through this. I want you to take a look at it, know that it exists. But we're not going to look at it here. Oh, and since we're at the end, the other thing these things are useful for, before all the modern instruments we have, one of the tests to see if we had an aldehyde or a ketone was to react with this thing, which is a hydrazine. And see, we have this nitrogen-nitrogen. It reacts to form this hydrazone and forms a very colored product. And that was used to be, before modern instrumentation, they would use this to show whether they had an aldehyde or ketone functionality in a molecule, because they would get this nice color change. Another interesting test before modern instrumentation, you can oxidize aldehydes to carboxylic acids with silver, and in the process you make metallic silver. Now if you do this in a test tube, you end up getting amine deposits on the side of the test tube, the silver deposits, so they would use that as a test. So we've pretty well finished chapter 16. You'll notice there's some other stuff here about spectroscopy. We haven't dealt with a lot of that lately. You guys have been exposed a little bit to IR. NMR we're going to do at the end of the class. This last, there we go, oops. These are the reactions we've did in chapter 16. And don't be don't be scared of them. Notice that a lot of them are the same, right? The mechanism, we did the same reaction about 15 times in the last week and a half. And that's going kind of from here to here. That part we do all the time. And then there's the added complexation, okay?